Hi everyone, I'm Won Lee. I have explained about capital X bar. Capital X bar is a sample mean and its distribution. Okay. Today's topic is a central limit theorem. It is very important theorem in statistics. Okay, let's see. Central limit theorem says regardless of distribution of population, what X. In other words, whether we know the distribution, of course, of x or not, whether we know f of x or not, the same wording, right? If if sample size is sufficiently large, that means n greater than equal to 30. It is from empirical study, okay? The distribution of a sample means approaches a normal distribution. Shortly, x bar follows normal distribution with mean mu variance sigma square over n. We studied these two terms yesterday. It is key theorem in statistics. Key theorem. If the population follows a normal distribution, x follows normal distribution with mean mu variance sigma square, then x bar, sample mean x bar, is normally distributed regardless of the sample size, no matter the sample size is. Okay? This one is key theorem. That's very useful in statistics. Example, suppose a certain population, X, has a mean 10, variance 2 square, standard deviation is 2, so sigma square is 4, right? And follow some distribution. We do not know the distribution of X, okay, from this population. If sample size 36 obtained, what is probability X bar greater than 9.5, less than 10.5? In this case, X bar follows what? Normal distribution, because the sample size is 36 with mean what? 10, and variance is 2 square, 4 over 36, right? Get it? So if x bar has normal distribution, when we have a normal distribution, then we first what? Standardize it. Standardize x bar here, standardize it here, x bar minus 10 divided by 2 over root 2 square root 36. Then this one standardized, then left hand side, right hand side values should be follow the same procedure. So 9.5 minus 10 divided by same thing, 10.5 minus 10 over 2 over 6, right? So this becomes z, this value minus 1.5, this value plus 1.5. Then what is it? You know that. 1.5 here. 0. This probability is area of from here to here, right? So 2 times this area. This area is 1.5. This one 0.4332. That's 0.8664. Okay, and if sample size is 64, then what is the same probability? This one, x bar between 9.5 and 10.5. The same procedure here. X bar is standardized like this, and left hand side, right hand side has what is the difference from this part? Here sample size is 36, here sample size is 64, only difference. So that is g greater than minus 2.0, less than 2.0. In this time it's going to be minus 2, 0, minus 2 plus 2 here is this area. Okay, so 2.0, the probability area is 4772 times 2 is 0.9544. It's simple, right? This is a simple example about the CLT. I'd like to repeat again. The mean and the variance of a sample mean x bar are always, anytime, expectation of x bar is mu. Variance of x bar is sigma square over n. Of course, this mu and the sigma square is population mean, population variance, respectively, right? Furthermore, from CLT, central limit theorem, we now know x bar follows normal distribution with mean mu and variance sigma square over n, right? This result. I think you better understand what I am talking about. Central limit theorem is the backbone of statistical theory. Very important. It is safe to say that most of statistical analysis method that will be covered in the future, okay, not now, are developed and based on normal distribution and central limit theorem. That's why it is very, very important. Okay, see this graph. Central limit theorem, distribution of x population, right? And the shapes of distribution of x bar based on different sample sizes. Okay, let's see this distribution. X is just uniform. We call it uniform distribution. X has something like this. Waiting time for subway that follow this kind of distribution. Then sample size 2, distribution of x bar is going to be like this, triangle. Distribution of x bar when n equal to 5, sample size a little bigger than before, then it's going to be like this, a little smoothed. And n equal to 30, the distribution of x bar is like this, bell-shaped, normal, similar to normal distribution. Okay, how can we get this kind of a graph? By what? Simulation. Okay, second example, if x population has a probability distribution function like this, okay, then n equal to 2, when n equal to 2, the shape is going to be like this. Of course, symmetric, but some funny distribution. N equal to 5, sample mean x bar is like this, okay? And when n equal to 30, distribution of x bar is like this, normal distribution. Even this way, population x has a distribution like this, like this. It is exponential or some reverse function. Anyway, like this, then n equal to 2, the sample mean follow this kind of distribution. N equal to 5, sample mean has this distribution. Sample size is 30, then distribution of x bar is going to be like this. Very close to normal distribution. So central limit theorem, we adapt central limit theorem here and there in statistics and play an important role in statistics. You get it? It is important, but not difficult at all. Okay? Okay, it's it. Thank you. Bye.